Good morning everyone. I'm Dr. Swathi, Pediatric resident from AIIMS New Delhi, and we will be discussing acid-base homeostasis today. The objectives of this presentation is to study the basic hydrogen ion kinetics, the buffer systems in our body, the regulation of pH change in our body, and related concepts such as the anion gap and the base axis, and few case scenarios after that. Coming to the basics, we all know that acid is any substance that releases hydrogen ion in a solution, and base is any substance that accepts the hydrogen ion. Hydrogen ion concentration in our blood is about 40 nanomole per liter. It can be difficult to express it in these units, and hence we express it as pH, which is the negative logarithm of hydrogen ions. And the rate of hydrogen ion production is 2 to 3 times higher in neonates due to the rapid growth and increased protein turnover and bone mineralization. So the normal pH ranges between the 7.35 to 7.45. When the pH is less than 7.35, it is called acidosis, and when the pH is more than 7.45, it is alkalosis. And when the pH falls below 7, there is severe acidosis, which can lead to multiple systemic involvement in our body, like CNS function deteriorates, there is poor myocardial contractility, and there is peripheral vasodilatation causing hypotension and shock. How is it that such a small ion, hydrogen ion, that is present in our body at such small concentration is able to bring about such big differences and changes systemic in the systems? So the hydrogen ion is capable of binding to proteins and can change their shape, configuration, and hence can alter their function. And since the most of the proteins present in our body are either enzymes, contractile elements, or transport proteins, any change in function of these protein components can lead to a huge change in our normal physiological functions. So now acid, as we know, it dissolves in a solution to release the hydrogen ion, and along with that a conjugate base. Now to decide whether the acid is a strong acid or a weak acid, we have to see the degree of dissociation. So here, as we can see here, a strong acid is able to dissociate almost to 100% and release a more number of protons as compared to a weak acid, which dissociates to a lesser extent and the protons released are lesser. Hence the pH change in this case will be lesser as compared to that of when a strong acid is added to a solution. And this degree of dissociation can be calculated using this dissociation constant, which is given by the products of dissociation divided by that of the acid. And the negative logarithm of this, which is the pKa, can also be used to assess the degree of dissociation and the strength of an acid. So as it is a negative logarithm, the more the pKa, the weaker is the acid, and the lesser the pKa, the stronger is the acid. Although hydrogen ion in our body is present at a small amount of 40 nanomole per liter, this hydrogen turnover per day is more than 150 mole per day. Hence, seeing this huge difference, we can understand that any difference, any small change in metabolism of this hydrogen ion can bring about a big difference in the hydrogen concentration in our body. So sources of fixed acids in our body are: by anaerobic carbohydrate metabolism we get the lactic acid, and by the incomplete lipid metabolism we get the acetoacetic acid and the beta hydroxybutyric acid, and by protein catabolism we get sulfuric acid and phosphoric acid. As we learned that the hydrogen ion is present in such a small concentration and the protein turnover is such a huge number, hence we have effective mechanisms to maintain the pH at such a small range of 7.35 to 7.45. These three mechanisms are: the first, the buffer system; second, the respiratory system; and third, the kidneys. Coming to the buffer system. What is a buffer? Buffer is anything that reduces the impact of a massive change. So in our body, buffers consist of any weak acid with a salt of its conjugate base. So for example, here the buffer system is a weak acid, which is the carbonic acid, along with the salt of its conjugate base, which is the sodium bicarbonate. So how does the buffer system work? Here, when a strong acid such as the hydrochloric acid is added to a buffer, it combines to form sodium chloride and carbonic acid. So here a strong acid gets converted into a weaker acid, hence the degree of dissociation is less. Hence the hydrogen ions that are being released is lesser and the pH change is not too massive. Similarly, when a strong base such as the sodium hydroxide is added to a buffer system, it gets converted into sodium bicarbonate and water, which is a weaker base, and hence the change in pH is again reduced. So the buffer systems present in our body are majorly in the extracellular fluid. We have the carbonic acid bicarbonate buffer system, and in the intracellular fluid we have the phosphate buffer system majorly. And the proteins buffers which are present both in the intracellular and the extracellular fluids are the hemoglobin, the amino acids, and the plasma proteins. Coming to the carbonic acid bicarbonate buffer system. So in our body we have a bicarbonate reserve which comes mainly from the kidneys. So here when there is addition of hydrogen ion or acidosis taking place, it reacts with the bicarbonate to produce carbonic acid, which is a weaker acid, and this can further be dissociated into carbon dioxide and water, as carbonic acid is a volatile acid, and hence the carbon dioxide is expired out. The carbonic acid bicarbonate buffer system prevents changes in the pH caused by fixed acids. It cannot protect changes in pH from PCO2 and requires an intact respiratory system to function. The carbonic acid bicarbonate buffer system is limited by the bicarbonate reserve that is present in the body. Coming to the hemoglobin buffer system. At a tissue level where there is metabolism taking place and carbon dioxide is getting produced, in the capillaries there are the RBCs with oxygenated hemoglobin that is coming from the lungs. So this carbon dioxide that is released through the metabolism diffuses out and into the RBCs and combines with the water present in the RBC, and with the help of the enzyme carbonic anhydrase gives a carbonic acid. This carbonic acid dissociates into bicarbonate and hydrogen ion. This bicarbonate diffuses out into the plasma, and the hydrogen ion makes the pH of the red cell and the surrounding tissues acidic, and hence releasing the oxygen from the hemoglobin to the tissues. Now the hemoglobin combines with the hydrogen ion to form the reduced hemoglobin. At the lung level, where inspiration is taking place and the oxygen is entering the lungs, and the blood is coming from the tissues to the lungs, and in the RBC there is the reduced hemoglobin. This oxygen that is coming from the lungs gets diffuses into the RBC and forms oxygenated hemoglobin, hence releasing the hydrogen ion. This hydrogen ion combines with the bicarbonate that diffuses into the red cell from the plasma and forms carbonic acid, which dissociates into carbon dioxide and water, and this carbon dioxide is expired out. Hence we can see that the bicarbonate which was present in the plasma, which was coming from the carbon dioxide at the tissue level, gets expired out as carbon dioxide at the lung level. Coming to the protein buffer system. The protein buffer system has the amine group and the carboxyl groups. When there is acidosis and the pH falls, the amine group as well as the carboxyl groups are capable of accepting this hydrogen ion and hence reducing the change in pH. And when there is alkalosis, the same groups are also capable of releasing or donating an hydrogen ion to maintain the pH. Coming to the phosphate buffer system, which is the disodium hydrogen phosphate or the sodium dihydrogen phosphate system. Phosphates are abundant within the cells and an important intracellular buffer system. So when there is acidosis or an acid is added into the body where there is increased hydrogen ions, it reacts with the disodium hydrogen phosphate component of the protein buffer system, which dissociates into sodium hydrogen phosphate and a single hydrogen ion. This combines with the hydrogen ion in the body to give a sodium dihydrogen phosphate, which is excreted in the urine. Now in cases of alkalosis, the sodium dihydrogen phosphate component of the phosphate buffer comes into action, which donates an hydrogen ion to maintain the pH in the body, and which later gets converted with the rest of the components get converted into disodium hydrogen phosphate and is excreted in the urine. So we learned about the buffer systems, and when the chemical buffers are alone not able to prevent the changes in blood pH, the respiratory regulation comes into action. This is the second line of defense. So here our lungs can maintain the pH by either eliminating or retaining the carbon dioxide, and these changes in pH are rapid and occur within the minutes. Here the amount of PCO2 present in our body is directly proportional to the amount of carbon dioxide that is being produced by metabolism, and inversely proportional to the alveolar ventilation. We can understand the respiratory regulation by these two basic principles, which is the chemical equilibrium and the law of mass action. Chemical equilibrium states that the rate of reaction in one direction is equal to the rate of direction in the opposing direction. So this does not mean that the concentration of substrates on the either side of the reaction are equal. It means that the direction of reaction in both the directions is equal, so has to maintain the components in the same concentration. So law of mass action is the change in equilibrium in response to a change in amount of one of the reaction constituents. So for example, to understand the law of mass action, there is acidosis and increased hydrogen ion concentration in the body. Then there is disturbance in the chemical equilibrium and the reaction shifts towards the left, and there is increased carbonic acid that is being formed, and this gives increased amount of carbon dioxide and water, and carbon dioxide is expired out. So this is how our body maintains the pH and maintains equilibrium. The third line of defense in our body is the renal regulation. In the renal regulation in acidosis, when there is increased hydrogen ion or decreased bicarbonate in the body, there is a secretion of hydrogen ions by the kidneys, or reabsorption of bicarbonate ion, or production of the bicarbonate ion to maintain the pH. And when there is alkalosis, when there is loss of hydrogen ion in the body or increased bicarbonate ion, there is decreased excretion of the hydrogen ions and decreased production and absorption of bicarbonate ions to maintain the pH. The bicarbonate absorption in the kidneys takes place in the early PCTs. In the proximal convoluted tubules, the carbon dioxide combines with water to give carbonic acid using the enzyme carbonic anhydrase, and this dissociates to give hydrogen ion and the bicarbonate, which is reabsorbed with the sodium bicarbonate cotransporter. And this hydrogen ion is pumped out into the tubular lumen using the sodium hydrogen pump. Sodium hydrogen pump is a secondary active pump which gets activated via the sodium potassium pump that is present on the basilar membrane. Here 3 sodium ions are getting reabsorbed and 2 hydrogen ions are being pumped into the PCT, as a result of which there is sodium deficit in the PCT, and this pump gets the sodium hydrogen pump gets activated at the tubular lumen. Now the hydrogen ion that is pumped in the tubular lumen combines with the bicarbonate that is coming through the glomerular filtration and gives carbonic acid, which dissociates to give carbon dioxide and water, and this carbon dioxide is reabsorbed into the PCT and converted into bicarbonate and reabsorbed. So here we can see that the bicarbonate that was getting filtered is ultimately getting reabsorbed here. And secretion of hydrogen ion is mainly taking place in the distal convoluted tubules and the collecting ducts. Here the hydrogen ion is getting pumped into the tubular lumen via the hydrogen ATPase pump or the potassium hydrogen pump, and is getting excreted in the urine. So we talked about bicarbonate reserve earlier, so let's understand that. In the liver, the amino acids are getting metabolized and there is production of glutamine. This glutamine in the PCT is acted upon by the glutaminase to give glutamate, and in this process one ammonium ion is produced, and this glutamate is further metabolized by glutamic dehydrogenase to give alpha ketoglutarate, and by this process another ammonium ion is produced. Ultimately, the alpha ketoglutarates get metabolized to give two bicarbonate ions, and this forms the bicarbonate reserve that is present in our body. This ammonium ion in the tubular lumen combines with chloride to form ammonium chloride and is excreted in the urine. Ammonia also acts as a buffer in our body. So as we learned earlier that the hydrogen ion is pumped into the tubular lumen by the hydrogen ATPase pump and the hydrogen potassium pump. This hydrogen ion combines with the ammonia to form ammonium, which cannot be reabsorbed into the PCT, and hence it combines with chloride to form ammonium chloride and is excreted out in the urine. So now let's understand the analysis of ABG. So when we see ABG, first we look at the pH. If the pH is low, there is acidemia in the body and there is acidosis, and this can either be due to a high PCO2 or a low bicarbonate. When it is due to high PCO2, there is respiratory acidosis, and when it is due to low bicarbonate, there is metabolic acidosis. And when the pH is high, it is alkaemia, and it can either be due to low PCO2, which is the respiratory alkalosis, or a high bicarbonate, which is the metabolic alkalosis. And when the pH is normal, it can either be a normal or a mixed acid-base disorder. Coming to the compensation. Compensation is the body's attempt to return the acid-base status to the normal, that is the pH that is closer to 7.4. So when the primary problem is respiratory, like suppose there is respiratory acidosis, then the compensation is via the metabolic alkalosis. Similarly, when the primary problem is a metabolic disorder, then there is respiratory system compensation. A rule of thumb is that the compensation cannot overshoot 7.4. The respiratory compensation is usually fast, occurring within hours, with like 12 to 24 hours, and the metabolic compensation is slow, taking days, 5 to 7 days. Now let's understand metabolic acidosis. Let's take an example of baby of A, born at 26 plus 3 weeks, and on day 5 of life developed pulmonary hemorrhage, shock, and progressive hypoxia. As a result of shock, there is decreased perfusion, hypoxia, and anaerobic metabolism taking place at the level of tissues, as a result of which there is increased decreased pH and decreased bicarbonate, and the homeostasis is disturbed. And now our three mechanisms come into action, which is the buffer system, the respiratory compensation, and the renal compensation. The buffer system tries to absorb the hydrogen ion and hence to decrease the pH change. And in the respiratory system, there is increase in respiratory rate, decreasing the PCO2, hence decreasing the PCO2 and increases the pH. And renal compensation acts by increasing hydrogen ion secretion or bicarbonate reabsorption. Respiratory compensation in metabolic acidosis is by hypoventilation to reduce the PCO2 and to increase the pH. The decrease in pH in metabolic acidosis is sensed by the central and the peripheral chemoreceptors, and that increases the respiratory rate. Increase in ventilation starts within minutes and is well advanced at 2 hours. Maximal compensation takes in 12 to 24 hours, as we have seen even earlier. The expected PCO2 can be calculated by the Winter's formula. The expected PCO2 in metabolic acidosis is equal to 1.5 into the actual bicarbonate plus 8 plus or minus 2. Coming to metabolic alkalosis, where there is loss of hydrogen ions or increased bicarbonate, there is increased pH and homeostasis is disturbed. And our three mechanisms come into action, which is the buffer system, the respiratory system, and the renal compensation. The buffer system tries to donate the hydrogen ions, and in the respiratory system there is decreased respiratory rate so as to increase the PCO2, and in the renal compensation there is decreased hydrogen ion secretion and there is bicarbonate decreased hydrogen secretion and bicarbonate reabsorption. So increased in pH is either due to increase in bicarbonate or decrease in acid, and respiratory compensation occurs by hypoventilation, and here the expected PCO2 can be calculated using this formula. Here for one rise of bicarbonate there is 0.6 mm of Hg of rise in PCO2, and the maximum compensation occurs up to 55 to 60 mm of Hg of PCO2. Coming to respiratory acidosis, now let's consider if there is a baby undergoing hypoventilation, then there is increase in PCO2 and decrease in pH and the homeostasis is disturbed, and the buffer system, the renal compensation and the respiratory compensation come into action. So compensation in respiratory acidosis. In acute respiratory acidosis, the compensation is mainly due to the intracellular buffering. For every 10 raise in PCO2, there is 1 millimole increase of bicarbonate, and the pH change can be calculated by 0.008 into 40 minus the PaCO2. And there is minimal increase of bicarbonate in acute respiratory acidosis. In chronic respiratory acidosis, the compensation is mainly via the renal compensation. There is acidification of urine and bicarbonate retention. So for every 10 mm of Hg of increase in PCO2, there is 4 millimole of increase in bicarbonate, and the pH change can be calculated by 0.003 into 40 minus PaCO2, and the maximum response of chronic respiratory acidosis occurs in 3 to 4 days. Coming to respiratory alkalosis, that can occur in hypoventilation when there is decreased PCO2 and increase in pH, and our three mechanisms come into action to maintain the pH, which is the buffer system, the renal compensation and the respiratory compensation. For the compensation of respiratory alkalosis, in acute respiratory alkalosis, the compensation is mainly by the intracellular buffering, and there is slight decrease in bicarbonate ion. This starts within 10 minutes and maximum response is observed in 6 hours. For every 10 decrease in PCO2, the bicarbonate decreases by 2 millimole per liter. In chronic respiratory alkalosis, it is mainly via the renal compensation. There is acid retention and bicarbonate loss. It starts after 6 hours and the maximal response is reached in 2 to 3 days. For every 10 mm of Hg of decrease in PCO2, there is a decrease of bicarbonate by 4 millimole per liter. Coming to anion gap concept. Anion gap concept can be understood with respect to metabolic acidosis. The basic principle of the human body is to maintain electron neutrality. That is, the number of cations in our body is equal to the number of anions in our body. And the measured cation in our body is the sodium ion, and the measured anions in our body are the chloride and the bicarbonate. So anion gap is nothing but the difference between the unmeasured anions with that of unmeasured cations, and the normal value is between 8 to 12 milliequivalents per liter. Coming to normal anion gap metabolic acidosis, which is either due to bicarbonate loss in the GIT or in the renal system. Here the chloride is proportionately increased to maintain the anion gap. So as we can see here, when there is bicarbonate loss, or a rapid dilution of extracellular fluid, there is increase in chloride proportionately so as to maintain the anion gap. In high anion gap metabolic acidosis, there is accumulation of fixed acids, as a result of which the bicarbonate is reduced in buffering them. However, there is no proportionate increase of chloride. Due to accumulation of unmeasured anions, the anion gap is increased. Coming to the metabolic indices we see in our EBGs, that is the bicarbonate and the base excess. The bicarbonate approach is also known as the Boston approach. The standard bicarbonate concentration is ranging between 22 to 26 milliequivalent per liter. And when this actual bicarbonate in our body is equilibrated to a temperature of 37 degrees Celsius and a PCO2 of 40 mm of Fe, we get the standard bicarbonate. This overcomes the changes in bicarbonate due to respiratory causes and reflects a non-respiratory acid-base change. Under ideal condition, the standard bicarbonate is equal to an actual bicarbonate. Analyzing the standard bicarbonate, so if the standard bicarbonate is low, then it is metabolic acidosis, and if it is high, it is metabolic alkalosis. Difference between actual bicarbonate and standard bicarbonate indicates respiratory acidosis if bicarbonate is more than the standard bicarbonate, and respiratory alkalosis if the bicarbonate is less than the standard bicarbonate. When the bicarbonate is equal to the standard bicarbonate, then the respiratory balance is present. The second metabolic index is the base excess, and it is also known as the Copenhagen approach. Buffer base is the concentration of all the buffers present in the body, and the total buffer base in a neonate is 48 to 49 millimole per liter. 50% of this is due to bicarbonate, and 25% is due to hemoglobin buffer, and the 25% is due to other buffers. Normal value of base excess is ranging between plus or minus 5. So actual base excess is equilibrated with temperature and PCO2, and the buffering capacity is due to bicarbonate and the hemoglobin in blood. However, in actual base excess, we assume that the concentration of the buffer base is equal in the intravascular as well as the interstitial component. However, it is not true, since the intravascular component has hemoglobin, and hemoglobin it contributes about 25% of the buffer base. Hence, to decrease this fallacy, we take the standard bicarbonate, which is equilibrated to a hemoglobin of 5 gram per dl. This value is brought about by if the intravascular compartment is diluted with that of the interstitial component, then we get an average hemoglobin of 5 gram per dl. Hence, this removes that fallacy of considering that all the components in our body, all the compartments in our body have the same amount of buffer base. Thank you.